Yes, I think recording has started. So if you look into this first diagram, right, here you see this when this clock is equal to 0, okay, say this is the clock, right, this is the clock. When this clock is equal to 0, then what is happening, this D, right, these been selected, right, means this input been selected, right, 0 1, so this is selected, so this is now connected with the output, right, so then Q become equal to D, right, okay. Now when this clock become 1, then what will happen, then this input has been selected, means this one input has been selected, and one input is basically nothing but is connected with this Q only. So that means what, whatever is there, that will be now remembered here, okay, right. So this is then the memory state, and then this is the transparent state, right, okay. Similarly, if you now look for the second one, right, here when you give again, if you consider this clock, right, if you consider now here this clock equal to 1, when the clock equal to 1, then what, then these two are connected, right, D is connected with Q, and when this clock equal to 0 next, then this output is connected with this, so that means it will go into the hold state. So there are basically two states. One is the transparent state. Transparent state means D is basically connected with Q, and the other one is the hold state, which will act as a memory, right? So you can also see from this, then a multiplexer, 2+1 multiplexer can be used as an latch as well, right? It can remember 1 bit. Okay. Now, okay, this is fine in terms of here. This is what actually. This is an gate level diagram, right? But what about in a transistor level diagram? Because ultimately we have to implement it in terms of transistor. Okay. Before we are going into this, then what is the difference between this number 1 and number 2? What is the difference between these two? So here you can see it is basically getting connected. D is equal to Q when clock is equal to 0, right? So this one is called negative latch, right? And here this D is connected with Q when this clock is equal to 1. So this is called positive latch, right? So negative latch, positive latch is fine. Okay. Now let us see the implementation. So this implementation is not difficult actually. If you can recall, while we are discussing then pass transistor and transmission gate, and we have seen like how means how easy it is to implement and marks by using a pass transistor or using a transmission gate, right? So here we are using this transmission gate only. So you see from here, this is one transmission gate, right? And this is another transmission gate. This is another transmission gate, right? Here we have given Q. This is the D input, right? Okay, let's see what is happening. Say when clock equal to, say when clock equal to 0, the clock equal to 1, say, that would be easier first. Say clock equal to 1. So when clock equal to 1, what will happen to this pass transistor? This is already 1. This is 1 bar. This means 0, right? So that means this is now transparent, right? What about this pass transistor? This pass transistor, this is clock is equal to 1. So that means this is 1. So this PMOS is off. This is clock bar. So this is 0. So this transistor is also off. So that means this is in an off state. That means there is no connection between this and this, right? So that means whatever is given to D, right, that will first get inverted, right, and then it will go here, right, and then it will again go do one more, means one more inversion, and it will be going to this Q. So suppose here D is equal to 1, then here it is 0, then after that the 0 become again 1. So this D is equal to 1 and Q is equal to 1. So that way our earlier this thing is valid. See, when this clock is equal to 1, right, whatever you give here in this D, that should be transferred to Q. Fine. Let's see the next case. When this clock is equal to 1. Now say here, now this, sorry, clock equal to 0. We have already discussed when clock is equal to 1. So when clock equal to 0, what will happen to this green transistor? Here clock equal to 0, so this transistor is off. This is PMOS, this is 1, so this is off. What about this? This transistor is on, this transistor is on, right? So you can see then D is now disconnected from this Q, right? However, there is a loop, and the loop is something like this, right? And how this loop is forming? This loop is forming like this, right? And you know, two inverter connected back to back basically act as a memory, right? So that way you can see like these two inverter can remember that whatever been stored here earlier, that will remember. You want to remove all the inverters. Yeah, if you want to remove all the inverter, then think what will happen, right? Then how do you store? Because a pass transistor, it cannot store that way, right? So basically you are storing in terms of in this bistable element. This is bistable element. This is actually the buffer only, right? Two inverters back to back means two inverters cascaded is buffer only, no? Right? Okay. So I hope this part is clear to you, right? Then this is what? This is basically actually this positive latch. Then if I ask you to implement this negative latch using pass transistor logic, can you do that? It's the same except you have to make this clock to clock bar to clock to clock bar, and that will do the what, right? Nothing else, right? Now, okay. Now the thing is that why while discussing pass transistor, we have also discussed this transmission gate, right? Why we have moved from pass transistor to transmission gate? Because there was an issue of 1 VTH drop, right? That's what we have shifted from pass transistor logic to the transmission gate logic, right? But what was the advantage in case of pass transistor logic? Number of transistor is half, because it is only if you are implementing only NMOS pass transistor, then it is only NMOS, PMOS only PMOS, right? So then if reducing the number of transistor is the prime important for you, then probably you can also implement the same circuit using the pass transistor, and probably you can see the circuit would look something like this. Let us take it whether this circuit is working as discussed like earlier or not. For example, say when this clock is equal to 1. So when this clock is equal to 1, right, then this is on. What about this is clock bar? So this is off, right? So this D, if this D is say 1, then here it becomes 0, right? Then you get here Q bar, right? If this D is 1, then you get Q bar is 0. Then you are getting Q bar from here. Okay. Now if you go use one more inverter, then you are getting here again 1, right? This is 1, this is 1, right? So whatever you have given here, so you are getting, right? Now let's see the other case when this clock equal to 0. So if this clock is equal to 0, then what will happen? Now this transistor, this clock bar, so this transistor will turn on, this transistor will now pass transistor will turn off, and you see basically you have this two inverter in a cascaded that loop, right? Bistable element. So now it can remember it or store the value, right? So here both Q and Q bar you should be able to get. So then this is what type of latch? Positive latch or negative latch? Positive latch, right? Okay. But what is the disadvantage? So the advantage is less number of transistor. What is the disadvantage? Disadvantage is this VTH drop. So, but the question is, say there is an VTH drop, but so what? We are still using some static inverters, right? That will make this drop, means that can compensate for this drop, right? Then why should we bother about this VTH drop? less noise margin. Yeah, less noise margin. Okay, less noise margin. Any comment on the in terms of power dissipation? Okay, let's do it here. See, say this clock is high. Okay, now this clock is VDD. That means clock is high means clock is VDD. What would be the maximum voltage that you can get here? It is VDD minus VTH. Right now, when it is VDD minus VTH, this is a static inverter. So static inverter means you have an PMOS and you have an NMOS. Right? Okay. So this is VDD minus VTH. Okay. Say this VTH is 0.6 volt. Say this VTH is 0.6 volt. And the threshold voltage of this PMOS, say minus 0.5 volt. Then when you have applied this voltage at this in this input, what will be the status of this PMOS? Is it on or off? Slightly on, right? It has just zero point 0.1 volt overdrive compared to, means it is above 0.1 volt overdrive than this threshold voltage. So there is a possibility then this MOS is then on. Okay, anyway, this is on, right? This is on. Now this is also on. So there is a static power, possibility of static power dissipation, right? So that is the reason why it is not good to have one threshold voltage drop at this output if you want to use that to drive an static inverter afterward, or static any gate, no, a static any CMOS gate after that, right? Okay. Uh, so far what we have seen is the latches, right? Where this whether it will store or remember or pass, it depends on basically the value, right? The level, clock level, not on the clock edges. But you know, to synchronize that particular logic with the other part of the circuit, it's preferred to have an edge triggered logic rather than an label triggered logic, right? You always want to be everything to be like triggered at this edge so that you can synchronize. So then whatever we have learned so far, based on that, can we think of doing something so that using two latches we can make an edge triggered circuit, means edge triggered memory element? That is the question. So for example, what is this first here? What is this circuit? This is latch. Negative or positive? This is negative, right? Okay. This is a negative latch. This is a positive latch. What if we connect this output with this input, right? And say now this is D, right? D input. Then see here what is happening when you have zero input. When this clock is equal to 0, this D is transferred to here, right? Okay. So that means you are now you are now in this region, right? You are now in this region, right? Then this is getting transferred to here, right? Okay. Now say what will happen when this clock will start rising at this edge, right? At this edge, what will happen? At this edge, this clock is now becoming 1 and this clock will go to, sorry, this clock will go to, right, this clock is becoming 1, this clock is also becoming 1, but then this clock will select this one, right, and this will go into this hold mode. And what will happen to this clock, I mean to this next latch? Here you have clock equal to 1. When clock equal to 1, this input is selected and this input is transferred to Q, right? So only you can see in this, during this age only, right, this D input would be able to transfer to this Q, right? Not here, right? Okay. Now what will happen? Okay, what will happen here in this region? Here clock is already 1. So clock is already 1. So whatever is coming here, that will still be connected here. But then what is happening to the first? It is still in this hold mode. So whatever it has stored, it will continue to hold, and this will continue to means continue to be in the transparent mode. Means whatever is there, it will continue be going to this output. Right? Now let us see one more case. Say for this, okay, when it was here, right, when this clock was 0, this was getting transferred to here, right? But what about this? Here this clock was also 0, but it was in this hold state. So whatever was the previous value, this is continue to hold at this queue earlier, right? So no data will be transferred before this positive edge. Is that clear to you? So that's how you can make an master slave positive edge triggered register. Now it is not a latch. Now it has become a register. We are not using this flip-flop term because flip-flop can be edge triggered, flip-flop can be level triggered as well. So to differentiate between latch and register, we are using here the term register, not the flip-flop. What about implementation? Means this is a gate level implementation, right? What about the transistor level implementation? You know, you can make this negative latch, you can make this positive latch. So if you can do that, then what is the issue? You simply, this is an you see, this is a negative, sorry, this is an first one is the negative edge, negative latch, second one is the positive latch, right? You just connect it like this. It's become like this, it's become like this. In one case, it will transfer to here. Very simple. Any doubt? Okay. So basically what we are discussing is this one only, right? We have an one master, the next one is the slave. Whatever is the input during this clock equal to 0, that would be transferred to here. When this clock become 1, right, it would going to remember that state, right? Okay. Now, and we have also seen the circuit. Fine. Okay. Now the question is, see this one, you will understand from here. This is the say that this is the clock input, right? And this is the D input, this data input. Okay, right. So the question is then, when this clock is during this positive edge, right? During this positive edge, before that, for some time, this data has to be stable. Can you see this? Before some time, the data has to be stable. You see, after this clock edge also, this data has to be stable, right? Do you agree with that from this? Now, why so? We will discuss the reason. Now, this particular time, okay, there are particular timing. Okay, what do you think? I mean, why do you think that this D should be stable for at least for some time before this positive edge of this clock? From this circuit, can you guess? Why? The question is why D should be stable. Right. In terms of this circuit, so it will pass through like which transistor, which inverter. Can you indicate that? Can you indicate that? Which it should pass through up to where? Okay, just tell me one thing. Before this positive edge, right? That this data should be available where? Till up to what point or what node? Till which node? till this QM, right? Till this QM. Okay. Now tell why do you think that the data should be stable for this much time? Because it has to travel through I1, this inverter, this transmission gate, then this inverter, then it would be available to QM. Is it all, or there is something else? It also has to be latch, so it has to also pass one more inverter. Not getting? See, because when this clock become 1, immediately what it will do, whatever has been stored here, means whatever been, suppose this D is equal to, say this D is equal to 0, right? Then that 0 have to be transferred to here, right? The same 0 has to be also here, right? Right, both side of this like transmission gate has to be 0 0, then only it will act as an latch, right? This one. So it would be the delay of this, delay of this, delay of this, and then delay of this, right? So this is basically that duration during which the D input has to be stable, at least for this time, for the reliable output or reliable performance from this MS master slave register, right? Okay. Now, why do you think there should be some time after this clock during which also the input should be stable? Same? No. Then explain why same. Which which inverter, which transmission gate it should be able to pass before that. Okay, here I think I should write one thing here. See, this time, okay, this time is called the setup time. Okay, this time is called the setup time. After that, it has to hold for some time, right? So that is from the name itself, it is the hold time. Okay, there is one more means term that is called the propagation delay, or yeah, that is the propagation delay, and that basically indicates the time, say, propagation delay. So any idea then why there should be like any hold time? Why the input has to be stable after this, means after this positive, even after this positive blockage? Right, right. But see, okay, let's consider this way. Okay, say these two inverters. Okay, say this inverter is not present. Just okay. Say this inverter, first inverter is not present. Okay, then whatever is change in D will be reflected immediately across this, right? Okay. Huh? Degrade to due to this T2. Uh, why? Okay, you were saying hold time is required because of T2. Okay, why? It has to pass through the T2, but it's fine, right? Here it is already 0. Here also it is already 0. So that is like we are not contradicting, right? Means suppose it may have some delay, but it will be 0 only. There is no issue, right? This is not going to change. Suppose now if there is any data, D has changed from 0 to 1. Will that affect this 0? Will that affect this 0? No, right? Okay. But just think about it. Say this inverter was not there. Say this inverter was not there. Okay. Then whatever be the change in D, that will be immediately reflected across this transmission gate. However, if you consider this clock, right, this clock or this clock bar is going through one inverter delay. Are you getting that? So there, this clock is coming, right? And it has to come through some, like through some inverters, right? So there will be some delay. So before that, before that delay, right? If you change the input, then what will happen? Your output can also get changed, right? But for this particular case, whole time is equal to 0, because you see it is the same thing, same time, right? So as soon as the here also it is one like one inverter delay, here also one inverter delay, right? Okay. Now there is one more term which is called the propagation delay. Propagation delay is what? It's the time required for this QM to go to this Q. Okay. So then what is the time required? For this inverter, this inverter, this inverter. Isn't it? Am I right? No, maybe not completely, because see this, okay, when this data is available here, right, we plus the delay of this, we have already considered within this delay, right, setup time delay. So this one inverter delay has, we have already calculated extra there, right? So maybe we can compensate that delay with this, because when this has to come transfer to this, during this time, this will be also be transferred to here, right? Then after that, it is basically the delay of this and delay of one more inverter, right? Okay. Then if there is like a question, something like this, D has been shown like this, right? That D is like 1 and D is 0, right? So that is because D can be 1, D can be 0, right? So if you are following this one, then just follow this. Okay. If you are following the lower one, D equal to 0 initially, then follow that one only. Similarly, this for QM. Okay, if for this, whatever you are getting QM, follow that QM only. You don't have to follow like both this and this. Same thing goes for this Q, right? Okay. So, and I hope that I don't, there is no need to explain this part, that, during this, during this time, the QM would be stable, because this would be in a hold state, right? So then definitely this is hold state, but this is not going to change, right? So here this Q is also not going to change. So it is going to stable during this time, right? Then after that, you can see the data is being changed during even this time. Data has been changed, but you see this output has remained still. The output has remained the same, because of what? Because now this QM can only change, right? But the still that positive edge has not come. So this will still be in this hold state. So this will be the hold state for this. This is the hold state for this, right? So as a result, for this entire duration, see, for this entire duration, you will be getting, the Q will be stable, right? Even though you can see here, there is a change in this QM, this internal node, right? No doubt. Okay, two simple things. This I think we should have discussed earlier. So this is the positive latch, right? It can implement it by using any like SL latch, by using by using this multiplexer based latch. That is up to you, right? So here you can see what this clock. This is positive latch, right? So when this is positive, right? Then only the data will be transferred to the. Am I saying the correct thing? What do you mean by positive latch? Data would be transferred during when clock is 0 or 1. When the clock is 1. Okay, let's see that whether it is happening here or not. There the clock is 1. Yes. Now the data has been transferred to this output. Right? When similarly the clock is equal to 0, data has not been, means it will be in a hold state. There will be again some delay, right? After that it will be in a hold state only. Okay. So here also you have noticed that this is the hold state, right? This is the hold state, right? And during this hold state, during this time, before that, before you reach to this, you see here also for some time, you should have D stable set of time. After this also, for some time you should have this input to be stable. Up means once you have reached this again, what? Oh, this is setup time. This is hold time. This is setup time, hold time. Then after that, you have also some propagation delay from this, right? Same thing you can also see from here, from the negative latch. So same thing you can also see from here, right? This is for this negative latch, right? So for here negative latch also you can see during this negative clock cycle, this input has been transferred to the output, right? So and this is what? This is actually the hold state, right? And during this hold state, you see before that data should be stable, input should be stable. After some time also the data should be stable and there will be some propagation delay, right? More details on this timing diagrams and all these things would be discussed in some type of advanced course, like particularly on digital IC design or some type of advanced level course. Okay, not here. Now, okay, so far what we have discussed are these static latches. Okay, they are basically static latch. So what do we mean by static latch? Static latch means it can hold the memory, the stored element until and unless you are interrupting the power supply, right? So that means if this is an static latch, right? This is an static latch and it can store the either 0 or 1 depending upon the input, right? Until and unless means until the power is there. Power means what? Power is the like that VDD. That VDD is there, it will remember it, right? So that's why it is called this. Right? It is basically the cross couple inverter, bistable elements, right? Okay. But if it happens that suppose we need some memory element where the store time is very small, means suppose you need to remember one bit for a very small amount of time, then probably we can think of something. If it is easier to design, right, where we will not store a bit permanently. Permanently means until the power is interrupted, but type of for a very small time. Say we will charge a capacitor. If the capacitor is charged, then we will consider to be as 1. If there is no charge in the capacitor, then we will consider the stored value is equal to 0. Then that is called as dynamic, register. So in dynamic register, what we will do, we will temporarily store the charge on a parasitic register. Parasitic resistor you understand, right? It may be the gate resistor, maybe the source to drain, uh, overlap capacitor, right? All this type of capacitors we will try to store this. Just see the value, see one diagram, it will be clear to you. For example, see this one, this dynamic edge triggered resistor. Okay, so here what we have done, we have used only one, this is one transmission gate, this is another transmission gate, this is an inverter, this is another inverter, right? Okay. And let's see that how this circuit can operate. Say this D is equal to 0, okay, and this clock is equal to 0. So clock equal to 0. When this clock equal to 0, this transistor is on, this is clock bar, this transistor is on, right? Now this D, whatever be the D, that will come here and charge this, right? So here basically 0. So basically this, if this capacitor was initially charged, now it will be discharged. To make our analysis bit simpler, let us say that here we have given D equal to 1. That would be easier. Say D equal to 1, right? Now this transistor is on, this transistor is on, this capacitor was initially discharged. This capacitor is the capacitor of this inverter only. It is not the any additional capacitor. Okay, so it will now go and charge this capacitor, right? Okay, now say in up, now it is 0, clock 0. Now here this clock become 1 at this age. So when the clock become 1, what will happen to this clock bar? This clock bar is basically now, let's say this is now clock become 1. So when this clock become 1, clock bar equal to 0, and then this become, this is clock, this is 1. What will happen to this clock bar? Clock bar will become 0. What will happen to this? This will become 1. So what will happen to this transistor? Off. What will happen to this transistor? Off. This transistor on, this transistor on. So whatever be the stored value here, the stored value is, say here 1, right? After that it has one more inverter, so here it is 0. So now 0 will be transferred here and stored here, right? So this is 0, this would be now 1, right? So you can see at this age, this input 1 would be transferred to this output Q, right? And when this transfer has been occurring, the transfer has been occurring in this positive edge only, right? So again, this is a positive edge trigger circuit. But what will happen to the charge stored? See, this is a capacitor, right? And this capacitor is charged only one time. You are not charging it continuously. So as the capacitor is charged only one time, then after that what will happen? It will, if there is any leakage path, definitely there will be leakage path, right? It will also going to discharge it, right? So that means an periodical charging of these parasitic capacitors are required. So that means there is a particular clock rate frequency is required, right? And this is possible in some applications. Suppose you are doing some arithmetic operation where continuously this D value is changing, right? You are continuously working on that, right? So what will happen during that time period? The charge loose by this capacitor or this capacitor would be so insignificant that you can consider the stored charge is equal to the logic, right? So there is a basic difference then where you can use this dynamic resistors and the static resistor. Static resistor is basically where there is no such restriction on this clock frequency, but on the power supply. But here you have some restriction on this clock as well as on this input D, so because you have to dynamically charge this capacitor before it discharge completely. If it discharge completely, then what will happen? This circuit will malfunction, right? And you can see there is no feedback loop, so it cannot restore its stored logic, right? So if it is lost, it will means it is permanently lost, right? But then what is the advantage? Okay, so you see previously this is one positive edge trigger circuit, How many transistors? Oh, this is too congested. How many transistors here? You have 1, 2, 3, 4, 5, 6, 7, 8, 8. Then 8 transistors. Then you have here 1, 2, 3, 4, 5, 6. So 6 inverters means 2 transistors. 6 and 12, and 12 plus 8, 20. Right? So you need to store 1 bit. How many transistors? 20. Okay. That is for the static case, master slave, right? Here, how many transistors? 1, 2, 3, 4, 5, 6, 7, 8. Right? So total number of transistors required is significantly lower for this dynamic logic, for the not dynamic logic, for the dynamic register compared to that of the static static register, right? So that is then obviously an advantage of means there is an obviously advantage. More transistor means more area, right? More delay, more power dissipation. However, there is some issues are also associated with this particular dynamic edge triggered register. For example, see here you need clock and also you need clock bar. So how you get clock bar? Basically, you take clock and use an inverter, get clock bar, right? So obviously, then these two would not be, synchronized. There would be some delay between this clock and clock bar. And if this delay is significant, for example, you see this is clock and this clock bar, then it can happen that for certain amount of time, you see here, like both clock and clock bar equal to 1. Here you can see both clock and clock bar equal to 0, 0. This is called the clock overlap, right? Here also you can see this 1, 1. Here also you can see 0, 0. This is called clock overlap, right? So if this issue happen, then see what is happening here. Say consider like a 0, 0 case. So when this clock is equal to 0, then this transistor is on. This transistor is also on. When this clock, what I am saying now, clock equal to 0, clock bar is equal to 0, right? So this transistor is on. So we have a direct path from Q to here, right? Now here also see clock bar is also equal to 0, right? Clock bar is also equal to 0 means this transistor is also on. So that means whatever you give at this input, that is that is transferred to this here, and as this transistor is also on, so that will immediately get transferred to this Q as well. So that means basically it is not becoming the edge triggered, right? So during that time there is a direct path from D to Q. But you think about the master slave flip flop. Master slave flip flop is what? There is no direct path from the input to the output, right? Only when there is a connection from the input to the mid in during one clock part, and the next clock part there is a connection between this mid part to the output. No direct connection between. Then the whole concept of this MS like master slave flip flop has been lost here, right? So this clock overlap. Huh? Right. That's what I said. Like if this is significant, right? Suppose this inverter delay is very small. Huh? If this inverter delay is significantly higher than this, then obviously this clock overlap does not play a much bigger role there, right? Okay. Now to stop that, this clock overlap issue, another type of circuit has been proposed, which is called C-square MOS register. So you are asking like so many type of we are like studying, right? Yeah, because all these things are there in syllabus. Okay, so it is the C-square MOS register. So what do you mean by this C-square MOS? So here you see this is the D input, right? So you apply this D input to this PMOS and NMOS, right? In the middle, you have two more resistor, but here you have connected clock and clock bar. So it is, you can compare it not 1:1 with the dynamic CMOS logic. There, the clock gated input was in the outside, and the logic was basically the inside. Here it is the opposite way, right? D is basically the logic is outside, and the clock gated inputs are basically inside, right? And here you can see it is basically the intermediate capacitor, which is the parasitic capacitor of this and this, and you have this clock bar and this clock bar. Now how this circuit operates? The operation of this circuit, say again, say D is equal to 1, okay, say now clock equal to 0, okay, so here clock equal to 0. So when this, what will happen to this clock bar? This is on, this is D is already 1, this D, this is on, then no, that means this is already on, right? So you can see this capacitor has a path through which now it can discharge, right? So then this capacitor will discharge and the voltage of this capacitor become equal to 0. Is there any path by which the capacitor can also charge? No. D is equal to 1, so this transistor is off. So there is no path for this capacitor to charge. So this value will be 0 only, right? So basically, have you understood one thing? Whatever you have given here, that inverted value is getting stored here, right? Okay. Now let's come. Okay. Now see what is happening to this when to the second part when this clock equal to 0. When the clock equal to 0, okay. When the clock equal to, this is clock bar, this is off, this is off, right? So that means whatever be the stored value in this capacitor, that is now completely disconnected, right? It has, obviously we should not bother what is this state or this state, because these two transistors are already off, right? So that means now it is can neither be charged nor it can discharge, right? It is type of isolated, so it will try to store its value, right? Okay. Now see the other case, when this clock become equal to 1. So when the clock become equal to 1, then what will happen to this? Clock equal to 1. So this is no, now earlier, yeah, clock. Oh, this clock, this is the clock, not this one. Okay, so the clock is equal to now 1. So this clock is now 1. So this transistor is now off. What about this transistor? This is clock bar. So this is now off. So this capacitor is now been isolated. Oh, cursor. Okay. Okay. 1 minute. Okay. So this clock is equal to 1, right? This clock is equal to 1 means this transistor is now off, right? This is now too thick. This is now off. This transistor is off. So this transistor is now, this capacitor is now isolated. It can neither be charged or not discharged. So whatever be the value, it will store, right? What will happening to the next second stage? Here you can see clock is equal to now 1. So clock equal to 1 means this transistor is now on. This clock bar is equal to 0. So this transistor is now turned on. Okay, this is already 0, right? Because it is storing the value 0 from the previous. And so now this 0 will make this transistor turn on, but this 0 will make this transistor turn off, right? So you can see here now there is a path for this capacitor to get charged. So now this capacitor will get charged and will store the value 1. So basically now you see it is getting one more time inverted, whatever be the value here, and that is been transferred to here. So we are getting that master slave action here, right? From here to here, and then from here to here, right? Now the question is why we are using this? To stop the that clock overlap issue. Now the understand whether that issue can still happen here or not. Okay, from this. Now say let us consider the 0 0 case. That means clock is equal to 0, clock bar is equal to also equal to 0. Okay, so clock equal to 0, so that means this transistor is on. Clock bar is also equal to 0, that means this transistor is off. Okay, now clock bar is equal to 0, so this transistor is on. Clock is equal to 0, so this transistor is off. Okay, now we have given here input, sorry, we have given here input 1, we have given here input 1 and 0 was stored here, right? So far that we know. Okay. Now we have given 1, so this transistor is now turned on. No, this transistor is off, this transistor is on. This 0 would help to turn on this transistor and turn off this transistor. Okay, now you see, is there any direct connection between this input D and Q? No. Do you agree with me? Middle point is floating. Yeah, middle point is floating. True. And suppose by any noise, okay, if this 1 0 become 1, is it still possible that like, is it still possible that if it suppose by, by some means, okay, uh, I think it's already 1. Okay, then can I discuss it in with some more time, because this cannot be discussed within, it has to be explicitly discussed in taking some more time. So we will discuss this part, this clock overlap issue, how this has been solved for 0 0 as well as for 1 1 case in this type of implementation in the next class. So next class is when? On 4th. Oh no, tomorrow. Oh, tomorrow we have a class, right? That is a 2 hours, right? And then we have one more class on 4th. 5th we have exam. So if we, that means maximum 3 hours. Okay, I need to finish SRAM. Okay, all these RAMs